Welcome and thank you for joining us. My name is Anne, and my teammates are Dawn, Olga, and Pauline. And together we developed Arroyo, a lightweight framework for the granular rehydration of logs. We're excited to tell you about it. We'll start off by introducing you to Memely, a fictional image and video hosting service. We'll talk about observability, and then we'll zoom in a little bit and talk about the ELK Stack and go over some existing solutions for rehydrating logs. After that, we'll introduce Arroyo and we'll go through some demos. During our technical deep dive, we'll explore how Arroyo works. We'll go through some of the engineering decisions we grappled with while we were developing Arroyo. And finally, we'll cover some of our future plans. We'll wrap up by opening the floor for any questions. Before we start, what is an arroyo? An arroyo is a dry creek bed or gulch that temporarily or seasonally fills and flows after sufficient rain. Similarly, our project Arroyo is a framework that performs rehydration. Arroyo rehydrates logs that have been stored in AWS S3. To aid with our presentation, our team would like to introduce everyone to Memely.com and its engineering team. Memely is a fictitious image and video sharing and hosting service that scavenges the internet to consolidate the most popular content being shared across the web. Memely strives to provide a one-stop shop for non-stop laughs. Memely.com was not an overnight sensation, but they now have a consistently growing user base. This has allowed Memely.com to start generating pay-per-click ad revenue by hosting clickable ads on its front page. The ad revenue has allowed Memely to reinvest in the site by hiring a small team of full-time developers. The Memely engineering team is currently focusing their efforts on scaling the Memely infrastructure to accommodate their growing user base. As the Memely team began scaling their infrastructure, they started to sense that they did not have the level of oversight desired to move forward confidently. The infrastructural complexity grew during the team's initial scaling phases. Eventually, a problem requiring an audit occurred. The ad agency that Memely.com hosts ads from has asked the Memely team to perform an audit to investigate potential click fraud that occurred on their site within the past month. In short, the number of clicks or user engagements with the ads that the agency generates and that Memely.com hosts well exceeds the historical amount for the site. How can Memely perform the click fraud investigation given the complexity of their infrastructure? Next, Pauline will cover what observability is and how it can help Memely perform their audit.
Thanks, Anne. Hi, I'm Pauline. I'll be reviewing basic observability concepts today. First, some definitions. To observe is to watch carefully. Observability is the ability to measure a system's current state using the data the system outputs. Note that observability is a property of a system, while monitoring is accessing the data provided about the system to make decisions. We use three types of data in observability that are sometimes called the three pillars. First, metrics provide the big picture measurements about a service captured at runtime. For example, the number of requests per second. Next, traces show the path a request takes through a distributed system. Finally, there are logs. Let's go into more detail. Logs are text records, ideally with a timestamp. They can be structured or unstructured. Logs often come with metadata and are usually the most finely detailed view of what is happening in an application. Logs are emitted by many applications. Because of the level of detail provided, logs are useful for both troubleshooting and auditing. However, logs don't scale well. Well, why not? How can we find the information we need when we are overwhelmed with a large amount of log entries? Ideally, we will need a way to centralize logs, search logs, and analyze the results of the search. One common way to manage logs is to use the ELK Stack. ELK Stack stands for Elasticsearch Logstash, and Kibana. Let's dive deeper into what this stack looks like. We'll start with Logstash, move on to Elasticsearch, and finish with Kibana. Logstash is a data collection engine with real-time pipelining capabilities. It has 3 stages: inputs, filters, and outputs. Inputs are where events are generated. In our case, the log files from every node. Filters are where we modify or transform those events. Here, we will transform the events from text files to JSON. Outputs are where the filtered inputs are shipped to. We will ship the JSON to Elasticsearch. Now, we'll review Elasticsearch. Elasticsearch performs many functions. Elasticsearch is a distributed document store, a real-time search engine, and an analytics engine. Let's break down the meanings of each of these terms. First, Elasticsearch as a distributed document store. Distributed means each Elasticsearch cluster has many different nodes for increased reliability. Document store means Elasticsearch stores serialized JSON files as complex data. Now, let's explore Elasticsearch as a real-time search engine. Real-time means it takes 1 second or less to index a document using an inverted index. Search means support for structured SQL-like queries, text queries, and complex queries that combine both. Finally, let's review Elasticsearch as an analytics engine. Analytics means creating complex summaries of data to gain insight into key metrics, patterns, and trends. Now, let's move on to Kibana. Kibana is a collection of graphical user interface applications that wrap around Elasticsearch. Inside Kibana, you can search data using Kibana query language, make charts and dashboards, and manage the ELK stack from a graphical user interface. Let's move back to Memely to see how they've implemented their ELK stack.
Thanks, Pauline. Memely has set up Logstash to transform text logs to JSON and send the transformed logs to the Elasticsearch cluster. Memely has Elasticsearch running on its own EC2 instance for better performance. Additionally, Memely has Kibana running on a separate EC2 instance. However, as the number of logs shipped to Elasticsearch increases, Elasticsearch is starting to run very slowly. Fast searching is a key benefit of Elasticsearch, but as the number of documents in Elasticsearch increases, searches become much slower. The stale documents, in order to keep searching fast, old or stale documents are removed from Elasticsearch using an index lifecycle policy. The stale documents can be stored elsewhere. One common choice is to store them in cloud storage. Memely decides to keep 2 weeks worth of fresh logs in Elasticsearch with stale logs shipped to an AWS S3 bucket. The decision to store 2 weeks worth of logs has been working well for the Memely team. Their ability to search logs is fast and reliable. They have the added peace of mind knowing older logs are stored in AWS S3, which is a cheaper and more secure storage option. Next, we'll explore how the Memely team can use their searchable logs within Elasticsearch to begin their audit. During a preliminary audit of their indexed web server logs, the Memely team noticed the following patterns. The donut chart shows us each client IP as a share of total requests to memely.com within the past 14 days. We'll notice one client IP holds a drastically disproportionate amount of weight within the number of requests that were made within the given time frame. At this stage of the audit, the Memely team chooses to focus their investigation around logs that involve this seemingly spammy client IP. Is the Memely team dealing with an extremely active user or something more malicious? The Memely team analyzed all of their indexed web server logs involving the specific client IP to understand how the client has been interacting with the website. The team discovered the following behaviors. All requests issued by this particular client were HTTP GET requests. All requests were sent to the root page of memely.com. where the majority of the ad's Memely hosts are served. Additionally, no attempts were made to browse the rest of the site as a typical user would. At this stage of the audit, the Memely team is confident they are dealing with a malicious user, reinforcing suspicions that Memely.com experienced bouts of click fraud within the past 30 days. The next question the Memely team would like to answer is, how long has this user been interacting with their site? Can the Memely team pinpoint when the suspicious behavior began in order to move forward with their audit? But because the Memely team decided to index only the most recent 14 days of logs, they don't currently have all of the necessary data within Elasticsearch to complete their audit. Ideally, what the Memely team would like to accomplish is to transfer the logs they currently have archived in S3 back into Elasticsearch in order to search older logs in a feature-rich, familiar environment while conducting their audit. The task of transferring archived logs back into Elasticsearch for easier searching is often referred to as log rehydration, and the Memely team has a few options at their disposal. Next, we will take a look at some of the existing solutions the Memely team could use to rehydrate their archived logs. There is no shortage of commercial observability solutions that offer log rehydration features. These are feature-rich, all-in-one solutions, meaning that users do not need to concern themselves with scaling complexities or infrastructure management. While a commercial solution is an option the Memely team could explore, they have reservations about cost, because they may end up paying for features that they don't currently need, complexity, because they would need to transfer all their current logs to a new, unfamiliar technology stack, and time, because it might take a while for the Memely team to get up to speed with all of the features offered, all this while attempting to perform their audit. If a commercial solution doesn't quite fit Memely's needs, there are many open source tools available to aid in their rehydration goals. The main benefit of a DIY solution is that the Memely engineering team could continue to use their existing ELK Stack and log archival solution. Another benefit is that the team could save on cost by looking to utilize free open source tools and plugins. However, because the Memely team is small, they may not have the time and resources to dedicate to researching all of the open source tools they could use to build a rehydration tool in-house. The scarcity of turnkey free rehydration tools is one of the primary reasons we decided to build Arroyo. So far, we've explored two options, the commercial route, the DIY route, and soon we'll explore Arroyo. Both the commercial route and the DIY route are valid solutions for log rehydration, but they don't quite fit the Memely team's use case. Ideally, the Memely team would like to strike a happy medium between the ease of a commercial solution and the ability to keep their existing ELK stack that a DIY solution offers. Another option the Memely team could explore is Arroyo. While Arroyo is not as feature-rich as a commercially available solution, the ease of use and ability to integrate with existing ELK stacks may make Arroyo the right tool for them. Next, we will explore Arroyo, highlighting what Arroyo is and how it might be used to help the Memely team rehydrate their logs. I'll hand it over to Don.
Thanks, Anne. So we hinted at log rehydration early in the presentation, and the first question we need to ask is, what is Arroyo? So to start, Arroyo is a lightweight framework for the granular rehydration of logs, and we're going to revisit this idea of granular rehydration a little further along in the demo. We allow users to search logs by date range or provide a date range and up to 2 queries to conditionally re-ingest logs, and those search results are pulled from S3 back into Elasticsearch. So let's take a look at Arroyo in action by going through a series of demos. Arroyo offers 2 options to facilitate the rehydration of archive logs back into a user's Elasticsearch. The first option is a bulk rehydration option. With this option, a user can specify a time frame and receive a list of log files that were inserted into their S3 bucket within that time frame. In order to generate this list of available log files, a user is going to need to specify the name of the AWS S3 bucket where their logs are currently archived while setting up and launching Arroyo, which we'll cover a little later in our demo. But from there, users can select from a list of available log files and re-ingest the entire contents of the selected files back into Elasticsearch. A great use case for the bulk rehydration option is when a user might want to reintroduce a batch of archived data into Elasticsearch in order to analyze trends or derive new metrics with some historical context. Let's take a look at how the Meanly team could use Arroyo's bulk rehydration to help with their audit. So within the Arroyo UI, a user can specify a start and end date, and from there they can select from a list of archive files that they would like to ingest. So for the Meanly team, they could select their Nginx logs. Now, once the job has been submitted, the Arroyo UI will notify the user that the task is in progress, and they'll also be notified once the job is completed, and they can return to their Kibana dashboard. So now that the Meanly team has a bunch of archive logs within their Elasticsearch cluster, they can continue with their audit. And as we can see, the Meanly team now has access to fully searchable logs within a time frame that was previously not present within Elasticsearch. While the bulk rehydrate option is a great tool for trend analysis and developing new metrics with some historical context, it does come with some trade-offs. So this donut chart was generated in the Kibana dashboard and represents the breakdown of the number of logs rehydrated during Arroyo's bulk rehydration job. The Meanly team wanted to rehydrate logs that were generated by the suspicious client IP that was identified during their audit, and they've managed to do so. But we'll notice that over 3/4 of the rehydration job includes logs generated by clients that the Meanly team is not currently investigating. So what this graph is a revisualization of these results with some added context, and that context being the impact on capacity, the size. So in order to generate this graph, we're making some assumptions. Let's assume that the Meanly team has performed multiple bulk rehydration tasks, and they've ingested around 10,000 logs. And each of these logs, each individual log line, is 297 bytes in size. What we're going to notice is that irrelevant data, or data that the Meanly team is not currently deriving any value from, is contributing 645 megabytes of capacity within Elasticsearch. To better suit the Meanly team's use case, it would be beneficial to rehydrate logs on a much more granular level, reducing the amount of excess data that's reintroduced back into Elasticsearch with each job, striving to rehydrate only the most relevant data. So let's rewind the clock a bit and demonstrate how the Meanly team could use Arroyo's query rehydrate option to get the information they need without any additional data bloat. With Arroyo's query ingest option, users can specify a time frame just as they would the bulk rehydration option. But then in addition, they're able to include 2 log attributes that they want to conditionally re-ingest logs based on. So for the Meanly team's use case, they could specify the spammy client IP as well as an HTTP request method of GET, since this behavior seems to be following a very specific pattern. Now, once the job has been submitted, the Meanly team could return to their Kibana dashboard and continue with their audit. Now, what we're going to notice is, given a similar time frame, in addition to being able to provide 2 log attributes, the Meanly team was able to gather the information they need without any excess additional data. And that's what that singular stick represents. It's only the information that pertains to that spammy client IP. So this donut chart was generated in the Kibana dashboard and represents the breakdown of the number of logs ingested during Arroyo's query rehydrate job. And as we can see, only the logs pertaining to the malicious client IP were re-ingested for this specific time frame. The ability to query logs before re-ingestion allows users a much more granular level of control with respect to the logs that they ultimately re-ingest back into Elasticsearch, which we think is a very important tool. So next, we'll take a look at index cleanup after a user's done using their rehydrated logs. One of the challenges using Elasticsearch is striking a balance between having too much information on hand and too little information. Naturally, rehydration reintroduces data back into Elasticsearch, which leads to some questions. What can a user do once they've rehydrated their logs and derived the information they need? Do these logs simply stay in Elasticsearch? And if so, doesn't that contribute to the problem that Arroyo is seeking to help solve? How do we reconcile with these questions? Arroyo provides a sample Logstash HTTP input template that users can implement into their ELK pipeline. The goal is to store all rehydrated information in a completely separate index compared to a user's day-to-day logs. That way, a user can simply delete the index once they're done using those rehydrated logs. So by default, if a user chooses to utilize the input template that the Arroyo team includes in our deployment repository, the rehydrated logs will be stored in a separate index called logs-arroyo. The template we provide is simply a guide, and users can tweak their Logstash HTTP input plugin as it suits their use case. Next, let's take a look at how to get started using Arroyo. To get started using Arroyo, a user will need to clone the Arroyo deployment repo available from our team's GitHub page, install the necessary node packages, and then follow the README instructions to provide the deployment credentials. Important things like your AWS credentials and your archive bucket name. But from there, the user can run Arroyo's deployment command in order to provision all the necessary AWS infrastructure Arroyo is going to need to perform rehydration tasks. Next, let's take a look at how to launch and get started rehydrating logs. So once the necessary AWS infrastructure has been successfully deployed, a user can simply issue the command docker compose up, and the Docker client will fetch and build the necessary images in order to launch the Arroyo UI and backend on their host machine. Part of launching the application will require the user to fill out an environmental variable file with information like the archive bucket name, which is where the user's logs are currently archived, and their AWS credentials. Providing these variables in an environmental file allows users to provide the minimum amount of information Arroyo will need to perform rehydration tasks. The goal was to keep this process easy. We wanted the AWS infrastructure deployment to be simple. And we also wanted launching the Arroyo UI and backend to be simple as well. So filling out one environmental file allows Arroyo to do everything it needs without much additional work from the user. So at this stage, let's assume that the users deployed all the AWS infrastructure. They've performed all the rehydration tasks that they needed to perform. What about cleanup? Let's take a look at how Arroyo can help in that department as well. So once a user has finished the rehydration tasks, they can easily unprovision the AWS infrastructure that was created during deployment by issuing Arroyo's destroy command. Once the destroy script has finished executing, all Arroyo created AWS infrastructure will have been destroyed, leaving no artifacts for the user to clean up afterwards. We wanted this entire process to be as easy as possible. Next, I'm going to hand the presentation over to Olga, who will give a technical deep dive into how Arroyo works, as well as some design considerations that we made along the way.
Thanks, Don. Now let's dive into Arroyo architecture and see how Arroyo application processes rehydration requests. First, let's take a look at a high-level overview of Arroyo application and AWS resources that are used by the application. During the installation, Arroyo provisions a number of AWS resources. This is done programmatically using AWS SDK. Arroyo provisions Rehydration SQSQ and Status SQSQ, as well as their corresponding dead letter queues. S3 bucket is created for hosting Lambda deployment package. Arroyo also creates an IAM role for Lambda function, along with appropriate permissions attached to it. Arroyo also creates the Lambda function itself. Both the Arroyo client and Arroyo server applications are containerized using Docker and Docker Compose. Conceptually, we can split our Arroyo application into 3 key phases: rehydrate, reingest, notify. Let's take a look at the first phase, which is rehydrate. During the rehydrate phase, the user first submits the request via Arroyo client, which is a React application that provides the Arroyo UI. Arroyo client then forwards the rehydration request to the Arroyo server, which is a Node application that interacts with AWS resources and facilitates rehydration and reingestion of logs. The request contains names of the files to be rehydrated, as well as some additional data about the rehydration request. For each file that needs to be rehydrated, server sends a message to the rehydration SQS queue. Within the body of the message, the server includes information about S3 bucket name, where logs are stored, key that represents the name of the file to be queried or fetched, Logstash endpoint, where the rehydrated logs will be forwarded to, and SQL expression, which is optional and will only be included if the user chooses to perform a query instead of rehydrating the whole file. Once the message is placed on the queue, Lambda function is invoked. Lambda will do one of two things. If message body contains a SQL expression, Lambda will use that SQL expression to query the file. Otherwise, Lambda will fetch the whole file. Now I'm going to describe how the file is queried in a bit more detail. We perform the query by utilizing Amazon S3 Select feature. S3 Select allows for filtering and retrieving data contained within an S3 bucket. It allows to query structured data using simple SQL statements. The log data stored in S3 bucket must be in JSON format. Although S3 Select also supports CSV or Apache Parquet, currently Arroyo only supports JSON format. To perform querying of the logs via S3 Select feature, we invoke Select Object Content action to create and submit a query request. This is done via AWS SDK. We send the user-generated SQL expression as a part of the request, and also specify that we would like any matches to be serialized and returned in JSON format. Once Amazon S3 receives the request, it parses the data into records and then returns the records that match the provided SQL expression. Being able to query log files allows us to retrieve a subset of the file contents and therefore reduce the amount of data that we reingest in users' ELK stack. Let's take a look at the next phase, which is reingest. During the reingest phase, Lambda makes a post request to Logstash endpoint provided by the user. Once the rehydrated logs are posted, they are forwarded to Elasticsearch by Logstash. After they're indexed by Elasticsearch, the logs are ready to be viewed in Kibana dashboard. But how does the Arroyo client know when the reingestion job is completed so that it can notify the user? Let's see what happens during the last phase, which is the notify phase. Once the logs are rehydrated and then forwarded to Logstash by Lambda, Arroyo application needs to be notified about the outcome of the rehydration request. After Lambda gets a response from Logstash, Lambda grabs the response data and packages it into a message. It then places that message onto a status SQS queue. The goal of the status queue is to hold the status of the reingestion tasks for the Arroyo server to pick up. At the same time, here's what happens on the Arroyo application server side. Once the Arroyo server finishes sending all of the messages to the rehydration queue, it starts polling status queue. For each message it receives from the status queue, it saves the body of that message and then deletes that message from the queue. Once there are no more messages on the status queue, the Arroyo server sends a single notification to the Arroyo client via server sent events. Arroyo client receives the notification event and then notifies the user via a toast message. Now the user can view their rehydrated logs in the Kibana dashboard. Let's discuss engineering decisions that our team had to make while developing Arroyo application. The first engineering challenge we had to solve was how to make sure that we rehydrate logs in a controlled manner and without overwhelming Logstash service. In order to reingest logs from S3, we could simply configure Logstash S3 input plugin to access the S3 bucket directly and reingest all of the logs that it contains. The problem is that we do not need to reingest the entire bucket contents. Instead, we need to be able to reingest the logs with precision. Potential alternative approach is to use an HTTP input plugin instead. With HTTP input plugin, we could send each rehydrated log or a whole log file as a post request. However, if we go this route, we can run into an issue. As the number of rehydration tasks and the number of post requests to Logstash increases dramatically, we could potentially overwhelm the Logstash service. For example, if the user decides to ingest thousands of files in a single rehydration job, with the current approach, we would have to send thousands of post requests, one right after the other. This may result in Logstash service getting overwhelmed. In order to solve this challenge, we considered a couple of different alternatives. The initial solution we came up with was to introduce Kafka into our architecture. Kafka is a distributed event streaming data store used for ingesting and processing of data in real time. Kafka would serve as the middleman between Arroyo application and users' ELK stack. In order to integrate Kafka, we would have to create a Kafka producer, and we would also have to configure Logstash to be able to accept Kafka events. In this case, we would have full control over which logs are ingested and also ensure that rehydration and reingestion layers are decoupled from the server logic. This approach would work well, but after conducting more research, we came to a conclusion that setting up Kafka producer is a non-trivial task. We decided to continue evaluating other options. The solution that we decided to implement was a combination of Amazon SQSQ and AWS Lambda function. SQSQ would serve as a buffer, and Lambda would perform rehydration and reingestion tasks. Now let's take a look at both of these technologies and discuss their pros and cons. Amazon Simple Queue service is a fully managed solution that allows to easily create, use, and manage a queue. Using a queue would allow us to create a buffer between the Arroyo server and the reingestion and rehydration layers. This would provide for better performance, scalability, and reliability of the whole application. Additionally, it is easily integrated with AWS Lambda, and it is fairly simple to create and interact with using AWS SDK. The downside of this choice is that introducing new components like SQSQ increases overall complexity of the application. AWS Lambda is a serverless compute service that allows to run code without provisioning servers. It is easily integrated with SQS. In our case, we were able to programmatically create both SQSQ and the Lambda, and then configure SQSQ as Lambda's trigger, so that once Q receives a message, Lambda automatically spins up and performs the rehydration and reingestion tasks. Benefit of using Lambda function is that it takes on rehydration and reingestion functions, therefore making our backend server more lightweight. The downside of using Lambda is that deploying Lambda programmatically still requires quite a bit of work. Once we decided that using SQSQ combined with a single Lambda works best for our use case, next issue we had to consider was how to ensure that the queue is not blocked by any problematic messages. The first approach we came up with was simply to add more error handling and retry logic to the server code. But upon further investigation as to what that logic should be, we realized that it might end up being very complex. The second approach we considered was using a dead letter queue. A dead letter queue is a queue that is created specifically to hold messages that can't be processed. It allows us to put aside messages that failed so that they don't block the queue. Also, having a dead letter queue makes troubleshooting of failed messages much easier. Once the main queue, in our case, rehydration queue, receives a message, it attempts to process the message a specified number of times. If the message processing continues to fail and message retention is set to a relatively long period of time, or volume of messages is large, there is a chance of failed messages blocking the main queue. Having a dead letter queue ensures that the main queue is not blocked and recovers quickly. While developing Arroyo, we faced the challenge of notifying the client once the rehydration job is completed. In order to achieve that, we needed to somehow access the result of each post request sent to Logstash, combine the results of all requests, and pass it to the Arroyo application. The first solution we considered involved setting up a webhook. A webhook is an API endpoint that would accept data payload from a different service, which in turn would trigger some other event. Our backend would expose an endpoint, webhook, that would accept post request. Each post request would contain a status of a single reingestion job. In this case, we would also need the user to provide a host or an IP address of the machine where Arroyo application is deployed. And then we would need to pass that information to the Lambda so that it knows where to post the status. This approach seemed like a viable solution. A downside of this approach is that notification layer would be tightly coupled with the rest of the logic. We decided to continue researching other options. The next approach we considered ended up being the solution we chose to implement. We decided to use an SQS queue. Once Lambda receives a response from Logstash, it would put a message containing the result of the request on the queue. The backend server would pick up and then process the message. Once all messages are processed, it would notify the client. One important positive of this approach is that if we were to build a more robust notification system in the future, we already have a way to access the status of each reingested log. Now I'm going to turn it over to Don, who is going to talk about future work.
Thanks, Olga. Some of the areas we would like to focus on in the future include, number one, being improved visibility into the jobs that Arroyo dispatches. Right now, the Arroyo UI will inform the user when a job has been dispatched and when it has been completed, but we would like to provide some additional insight into the overall process. Another area we would like to focus on in the future is more robust searching capabilities. While we currently support searching logs that are formatted in JSON, we would like to expand that ability to perform full text log searching. We would also like users to be able to perform more robust query searches by expanding the number of log attributes each user can specify and implementing some additional logic to perform more complex queries. Finally, we would like to expand our integration capabilities and be able to fetch logs from multiple cloud storage vendors. The goal would be to increase flexibility and be able to expand the benefits of log rehydration to a wider range of users. So that concludes the informational section of our presentation. Next, we're going to hold a brief Q&A, so if anybody has any questions they would like to ask the team, now is the time to do so. And what I'm going to do is open up the Q&A and the chat sections. So we have one from Elaine that says, how did we come up with the idea to build Arroyo?
I'll take this one, Don.
Okay.
So while we were researching, we found a blog post written by Netflix about creating their own observability tools. In this post, Netflix writes about choosing to stream logs as events and only persisting selected logs in memory in order to deal with the large amount of log volume Netflix generated. We became curious as to how else this problem of log volume could be solved. Commercially, some observability platforms offered to store stale logs on a cloud storage solution for some time for an extra fee, but only a select number of these solutions like Datadog, Logzio, etc., offered the ability to search and restore these logs. And we did not find any open source solutions with this capability, so we knew that it was a good use case.
Okay. Well, if there are no more questions, on behalf of Team Arroyo, I'd like to thank everybody for stopping by and letting us show you all the work we've done over the past few months.